Hello everyone, my name is Fong. I'm a PhD candidate at Stony Brook University. Today I will be presenting our paper with the title Domain Name Encryption is Not Enough, Privacy Leakage via IP-based Website Fingerprinting. This is a joint work with researchers at Stony Brook University and UMass Amherst. Online surveillance is prevalent, and most internet users are not aware of privacy and security risks when using the internet. So when it comes to surveillance, China is one of the most notorious countries that has been making use of technologies for large-scale surveillance. Even in many Western countries, including the US, where privacy laws have been long established, online surveillance by private companies is still an ongoing problem. So online surveillance has led to severe violations of many human rights, including the rights to privacy. And as a result, more and more network traffic get encrypted on the internet to improve the security and privacy for internet users. Just to give a sense of how encryption has increased over the years, this plot shows that all traffic of major Google services are now encrypted, with some of them were not widely encrypted just 5 years ago. Here is another picture from the Internet Archive project showing that almost 90% of URLs crawled by this project, starting with HTTPS. This is an increase from just about 20% 5 years ago. So this increase of encrypted traffic is thanks to free 2S certificate authorities like Let's Encrypt. As you can see, just within the last 5 years, Let's Encrypt has issued free certificate for almost 250 million fully qualified domains. And this is an amazing scale for free service because certificates used to cost money. And regardless of the expansions of HTTPS traffic, plaintext domain names are the last piece of unencrypted information that is still largely visible on today's internet. So where is domain name information exposed? This slide shows us the common places where domain name information can be monitored by an on-pad observer. So these are the packets captured when visiting example.com. The first place where the domain name example.com exposed is through the DNS query and response. And after getting back the IP address of example.com, the client initiates connection support 443 and starts the 2S handshake protocol. This is the second place where domain name information is exposed. This is because the 2S handshakes take place before the actual encryption happens, and therefore exposing the domain name information in one of the 2S extensions called server name indication. So the exposures of domain name information in these two channels have led to many security and privacy problems. For example, domain names often reveal some semantic information about the website being visited. For instance, your online shopping preference, or maybe health conditions, religions, gender identity, or even worse, sexual habits. And since the traditional designs of DNS is in plaintext, this information has been given for free to any on-pad observer. For example, internet service providers can use this information for targeted advertisements. And that's why when domain name encryption is proposed, there has been some pushback from many internet service providers. So let's discuss in more details about domain name encryptions, which include several proposals and implementations. First, we have DOT, in which DNS queries and responses are transmitted through a TLS channel. With DOH and other implementations of DNS encryptions, the DNS resolutions is performed over HTTPS and therefore inheriting all security benefits of the HTTPS protocol. And starting from TLS version 1.3, the server name indication extensions in the client hello during the TLS handshakes can be encrypted too. With these proposals, the domain name information in both DNS and TLS handshakes traffic can be secure. And in the new setting, the users and the DNS resolver first establish an encrypted channel, which could be over HTTPS or TLS. After that, DNS queries and responses are sent over this channel. And during the TLS handshake, unlike in previous versions, from version 1.3, the server name indications can be encrypted. And this new proposal prevents any on-pad observer from seeing the domain name information. However, IP address of the destination's web server is still visible to the observer. And this motivated us to investigate whether domain name encryption actually improve privacy or not. In particular, we investigate the extent to which browsing tracking at scale is still possible based on the relationship between domain names and their hosting IP addresses, which are still visible to any on-path observers. And the extent to which this inference can be made depends on two factors. First, whether the domains are co-hosted with many other domains on the same IP address or not. Second, the stability of mappings between domain names and their hosting IP addresses over time. So to track online activities of internet user when all network traffic is encrypted, website fingerprinting is often employed. Website fingerprinting is a type of traffic analysis attack which is used to construct fingerprints for a set of websites based on the traffic pattern observed while browsing them. And depending on which metadata is visible from the encrypted traffic, different techniques can be used to determine whether a user visited any of the monitored websites. And as IP address information is still visible, we introduce a lightweight website fingerprinting technique that allows a network level observer to identify with high accuracy the websites a user visits based solely on the IP address information. So this is an overview of our method, which I will walk through step by step in the next coming slides. So first, for our test list, we curate by getting 100,000 most popular domains from the trend code list. We then complement it by also taking 126,000 sensitive domains from the Alexa list. The rationale here is to have a balance among different types of websites and to not only consider popular websites, but also the sensitive ones. And in total, we crawl 220,000 websites, and of which we could successfully crawl more than 208,000 websites. This is because some website was not responsive at the time of our study. Next, when crawling this 220,000 websites, we extract the domain names contacted to download the web resources. This makes a set of unit domains for each website that we call a domain-based fingerprint. This is an example of a domain-based fingerprints for twitter.com, which include two parts. The primary domain, which is the one that we type in the URL bar. And the second part is a set of secondary domains, which are contacted to download all the web resources for rendering the website on our computer screen. So from the domain names collected, we then conduct DNS resolutions to obtain their hosting IP addresses. We repeatedly conduct DNS resolution to capture all possible IP addresses of the domains. This is an example of domains to IP mappings that we have collected with each IP address is shown as an integer here. So for instance, we observe 4 different IP addresses for the domain twitter.com and similar for other secondary domains. We then construct the IP-based fingerprints. From this domain-based fingerprint, the first part of an IP-based fingerprint is a set of IP addresses of the primary domain. And then the second part of the IP-based fingerprint is a set of IP addresses of all secondary domains. So as an on-path observers, we then sniff for IP addresses contacted when each website is visited. For instance, this is the sequence of unit IP addresses captured when twitter.com is visited. And now to identify which website the sequence of IP address captures above belong to, we scan that sequence of IPs against the sets of IP-based fingerprints that we have constructed. So we first scan the first IP address in the sequence against the primary IP address in the fingerprints. And if there's a match, we continue scanning the second part of the fingerprint for matching secondary IP address to find the best matching fingerprint. In our initial work, we know that many websites are hosted on an IP address that does not host any other websites. For instance, these are such websites, and this includes some very sensitive websites. So when a primary domain is single hosted on one IP or multiple IPs without sharing the hosting servers with any other domains, it is straightforward to infer the website being visited. So we have shown in 2 slides before of how we match the fingerprint. Now, if a website is single hosted, we only need to scan and match the primary IP address. And from our data, we find that 52% of website studies have their primary domains hosted on their old IP addresses. And as a result, an adversary could already infer 52% of the targeted websites based solely on the IP address of the very first connections to the primary domain without having to consider the secondary connections. And then by also considering secondary connections, we obtain an increased matching rate of 84% among the fingerprinted websites. We could match 92% of popular and 78% of the sensitive websites. A more worrisome result here is that 95% of sensitive and popular websites can be fingerprinted. And until now, we have put all of the secondary connections into one set, which does not have any order. However, when viewing the whole rendering process, there is a loading order which we can rely on to cluster connections into groups. And this order is known as critical rendering path. In other words, there are some critical web resources that must be loaded before some other resources. And as you can see in this example, there are 3 clusters of connections. And these clusters are closely related to the critical rendering path, which each cluster happens after a specific rendering event in the browser. So clustering connections like this helps improve the fingerprint discriminatory capacity. And here is how the enhanced IP-based fingerprints look like from the domain-based fingerprint that has been clustered. We then obtain the enhanced IP-based fingerprint, which look like this. And for the sequence of IP address captured from network trace, we use k-means clustering, cluster them into 3 clusters based on the time when each connections were initiated. And then we scan this sequence of IP address against the fingerprints that we constructed. We first scan the primary connections, and then the first cluster of connections, followed by the second cluster, and finally the third cluster. This is similar to walking through a decisions tree, and this enhanced fingerprinting techniques helps increase the matching accuracies. So with that technique, we can improve the accuracies to 91% for the popular and sensitive websites. We obtain an accuracy of 96% and 87% respectively. An alarming result here is that 99% of sensitive and popular websites can be precisely fingerprinted, posing a serious privacy risk to their visitor. And to examine the stability of our fingerprints, we conduct our measurements in a longitudinal manner for 2 months. And we show that our enhanced IP-based fingerprints are still effective at identifying about 70% of tested websites. And to evaluate the robustness of our fingerprinting technique, we next consider a more realistic scenario in which HTTP caching is taken into account. And we find that an accuracy of 80% can still be obtained when a website is revisited within just 5 minutes from the first visit, meaning that most web resources are loaded from the browser cache. Next, to simulate the use of ad blocking, which is often used by many privacy-conscious users nowadays, we also conduct our experiment with the Brave browsers, and as a result, ad and tracking domains are blocked, leading to change in the loading orders of web resource and fewer observable IP connections. However, we could still obtain an accuracy of 80% when employing the basic fingerprint technique, in which the ordering structure of loaded web resources is not considered. So the key takeaway from our study is that regardless of the increasing trend of co-locations on the web, domain name encryptions cannot provide meaningful privacy benefit with the current degree of domain co-hosting, since the IP address information is still visible to any on-path observers, and that information can be used to infer the website being visited, allowing browsing tracking at scale. To that end, we make the following recommendations to improve the privacy benefit provided by domain name encryptions. First, the full domain name confidentiality must be preserved on both DNS and TLS traffic. Otherwise, neither technology can provide any actual privacy benefit if deployed alone. Currently, we are seeing a lot of effort to deploy DOH or DOT by several internet companies, including Firefox, Cloudflare, Google, and Microsoft. However, to the best of our knowledge, ESNI has not been equally considered and it is still being developed as an internet draft. And for domain name owners, they can choose providers that offer a high co-hosting degree per IP address or highly dynamic domain to IP mappings. And finally, hosting providers can help to increase the co-hosting degree by grouping more websites under the same IP address and frequently rotate domain to IP mappings to further improve privacy benefit offered by domain name encryptions. And that's conclude my talk, and thank you for your attention.